We present Saft, shape and appearance of fabrics from template, via differentiable physical simulations from monocular video. We designed a method to reconstruct the 3D geometry and appearance of moving fabrics from a single RGB video. We tackle the depth ambiguity problem by analyzing its source and designing two novel regularization terms to alleviate the consequences. Our pipeline needs RGB video data together with corresponding masks and the camera parameters. Moreover, we require a template mesh of the initial state as reference and as a starting point for our physical simulation. Our method consists of three phases that all make use of a gradient-based optimization scheme. First, we perform a projective texture mapping to ensure perfect alignment of the texture on the template mesh. Second, we optimize the cloth geometry by employing a physical simulation as a backbone. Lastly, the reconstructed geometry is used in further applications. We decided to estimate the optical material of the cloth, but due to the now known geometry and the opportunity to manipulate it via the physical simulation, many other applications are possible. Our pipeline first begins with the texture projection step, in which the cloth texture is optimized such that the rendered image has to match the target image for the initial frame of the video sequence. The required template mesh ensures that the textured 3D model matches the real fabric as closely as possible. We interpolate holes in the texture by adding a smoothness regularization to the loss function. The geometry reconstruction is the core of our method, and features a differentiable cloth simulation that deforms the mesh geometry over time. Similar to the texture in the previous phase, there are several simulation-related parameters which control the dynamics, by changing how stiff the cloth behaves and which external forces are acting on it. After the simulation steps, we employ the differentiable rasterizer NVDiffRast to render RGB and mask images. These images are then compared with the target video and masks to compute standard image losses. We backpropagate the loss gradient to the physical parameters that adjust the motion to match the target images. Unfortunately, without any regularization, strong artifacts appear as if the cloth was crumpled instead of moved. These errors do not only impair the reconstruction quality, but also create visibly unrealistic artifacts in the renderings. Our main contribution is an explanation for this behavior and the introduction of two regularization terms that counteract this problem. So let's give an intuition of why this happens based on an idealized example. Let's suppose we render the cloth, visualized by this grid, at some time t1, and it matches the real cloth that we want to reconstruct. Now, the target cloth moves backwards, and at a time t2, it appears smaller in the image, because it is now further away from the camera. We want the same thing to happen for our digital cloth mesh and therefore backpropagate the loss gradients. In the ideal case with perfect correspondences, the image gradients would look like this, where each mesh vertex is guided towards the correct 2D position in the image. Now, these gradients are backpropagated through the rendering process into 3D, without any depth information along the viewing direction. We visualize this from a top-down perspective and conclude that gradients in 3D space lie perpendicular to the viewing direction, because this is the direction of greatest change regarding the final image loss. We can also prove this mathematically, by expanding the loss gradient with respect to some arbitrary variable q, into three different parts: the gradient of the loss with respect to the pixel coordinates, the gradient of the pixel coordinates with respect to the camera space vertex coordinates, and the gradient of the camera space vertex coordinates with respect to q. Note that we have to sum over all pixels with coordinates px, py, and all mesh vertices at positions x, y, z, that are influenced by the parameter q. The important part involves the first two terms. The first gradient is unimportant for the derivation, and we simply replace it by a vector with two components a and b. The second gradient, the gradient of the pixel coordinates with respect to the camera space coordinates of a vertex, can be computed explicitly using the OpenCV convention we are using, resulting in a 2x3 matrix, including the camera's focal length, as well as the vertex position. Together with the first gradient, we obtain a general expression for the three-dimensional gradient of a rendered vertex. A simple dot product with the viewing direction, again in camera coordinates, immediately shows the orthogonality between these two vectors. This result is independent of the context and applies to other rendered geometries as well, like point clouds and splatting techniques. However, the only part that can break this orthogonality is the third gradient, which originates from computation in the forward pass before the rendering projection step happens. In our case, this is the physical simulation that introduces a coupling between neighboring vertices and make them share gradient information with each other. However, neighboring vertices are only able to provide little gradient information along the viewing direction, and therefore we obtained lots of artifacts without further regularization. Hence, we introduced two regularization terms to improve the situation. First, we treat the symptoms by guiding the geometry towards its undeformed state and thus actively prevent the cloth from crumpling. In particular, we penalize stretching, bending, and shearing of the cloth during the whole sequence by reusing the corresponding energy terms from our physical simulation. All details on that are provided in the paper. The second regularization term treats the source by penalizing the external force components perpendicular to the viewing direction. This effectively dampens these vector components such that their magnitude becomes more similar to the gradient along the viewing direction. Both regularizations are specifically designed to match our use case, but we are sure that they can be adapted to benefit other methods and applications as well. A direct comparison of the reconstructed geometry with and without these regularization terms shows their efficacy despite their small contribution to the overall loss function. Both terms are scaled to be 1 to 2 orders of magnitude smaller than the image loss and still make a huge difference. The last phase in our pipeline leverages the reconstructed geometry and infers the appearance of the fabrics by estimating the SVBRDF and environmental lighting conditions. This is just one example of further applications in which high-quality geometry is necessary to obtain good results. In order to optimize the appearance, we switch from a rasterizer to the differentiable ray tracer NVDiff-Rec-MC. For optimizing the diffuse roughness and metallic textures, we rely on existing work that models them using a decoder neural network, which is more stable than optimizing the textures directly. The estimated SVBRDF then enables applications like relighting of the object. We evaluate our reconstruction method on the phi-SFT dataset, and compare the results to phi-SFT itself and the method physics-guided shape from template, which we abbreviate with PGSFT. The dataset contains 9 sequences of real-world fabrics with various different dynamics. Here we show the target video and the renderings of each method in the top row, and the corresponding difference images in the bottom row. The mean squared chamfer distance is also shown for each method and each scene. We obtain more accurate geometries than phi-SFT and PGSFT, which also leads to renderings that are closer to the ground truth video. The evaluation of other metrics yields similar results, and they are all given in the supplementary material of our paper. The dataset also provides depth data which is not used by any of the methods, but but enables further evaluations to compare the results. Here we show depth images, depth difference images, mesh views, and novel views for all three methods. The depth difference is colored in red when the reconstructed geometry is further away from the camera than the ground truth geometry, and blue when the reconstructed geometry is closer to the camera than the ground truth. On average, our method reduces the 3D reconstruction error by a factor of 2.6 and 2.9 compared to the other methods. With an average reconstruction time of 30 minutes per scene, we are also much faster than Phi-SFT but slower than PG-SFT. The latter one was designed to work as quickly as possible at the cost of overly smooth reconstructed geometries. Our method now combines high-quality reconstructions with a moderate runtime. An ablation study for our work shows that the two regularization terms have a great impact on the reconstruction quality, which we already saw before visually. However, for some scenes, the ablated versions perform even better than our full model. This mainly comes from the variety of motions across the different scenes and indicates that further quality improvements are still possible. Lastly, we evaluate the appearance reconstruction employing our reconstructed geometry. A comparison of the final renderings with the target videos shows great similarities. Unsharp regions or small mismatches are mainly caused by deviations in the geometry reconstruction. Nonetheless, looking at the SVBRDF and environment textures directly, we observe some unexpected results, despite having nearly perfect renderings. While the roughness and metallic textures are supposed to be very uniform, we see imprints of the fabric textures in them. Furthermore, the diffuse color is leaking into the environment map to match the colors in the target video. We analyze these effects by creating 5 synthetic scenes with known geometries SVBRDF and environment maps, 2 of which are shown here. The synthetic scenes enable us to differentiate how large the influence of the geometry on the appearance is. In such cases, the appearance estimation with and without ground truth geometry yields very similar results, with unsharp and slightly distorted regions being expected due to deviations in the reconstruction. However, imprints in roughness and metallic textures, as well as color errors in diffuse and environment map are still present, although we have access to the ground truth geometry. This study shows that in these cases the reconstructed geometry is not the limiting factor and that an estimation from a monocular view is a highly underconstrained problem. More details on the appearance estimation and all results are given in the paper and its supplementary material. Thank you for your attention, and take a look at the video description for links to our project page and the GitHub repository.